Hi, today we're going to be talking about the terms concentration and dilution. And so because we're talking about concentration, I thought there'd be no better way to start off than by putting the thinker up there, of course, which is a great symbol of concentration. But of course, the concentration we're talking about is a little bit more like the concentration you would think about when you imagine drinking a cup of Kool-Aid. Okay, sometimes you'll have very concentrated Kool-Aid that tastes very strong, and other times you'll have very dilute Kool-Aid that tastes kind of weak and watery. Okay, let me give you another image to think about concentration, to think about what we're talking about here. So in this image, see if this works. Okay, in this image, of course, we have a very crowded swimming pool. And we might say, how do we describe a crowded swimming pool? And you could also say that a swimming pool is very concentrated with people, okay? So you might come home and you might say, okay, this swimming pool had, let me see if I can get this 1 second. This swimming pool had 100 people per pool. Okay, that'd be one way to describe it. Okay, but what if those people were quite big? Okay, because that'd be very different if it was filled with big people than if it were filled with very small people. So if they were big people, let's say they averaged 200 pounds, okay? Then we might be able to describe it a little bit differently. We could say it's 20,000 pounds, LBS, per pool. Okay, so that would be one way of describing it. Okay, but what if we said, okay, take all of the mass of what's inside of that pool, okay, including the water and the people, and say, okay, what percentage of that, let's call that a solution, okay, because a solution is a mixture between a solvent, which in this case would be water, and a solute, in this case would be people. And let's say we were trying to figure out, okay, what percent of the mass of that pool is people, and what percent is, or what's the total, okay? So what we would do here is we would take, we're going to use, instead of technically mass, we're going to use pounds here because we started off with that. So we're going to say it's 2,000, or 20,000, my mistake, pounds. And let's say the total weight of the pool and the people, and that's, in other words, that's the solution, the total weight of those. Let's say that was 100,000 pounds, okay? So if we took this 20,000 divided by 100,000, we would get 0.200. And if we multiply that fraction by 100%, okay, then we would get 20%. Okay, so we would say 20% of the mass of that solution. And when I say solution, I mean the pool and the people. 20% of that is people. So it's 20% people by mass. Okay, so you can see there's different ways of describing how crowded a pool is. Okay, we just say it's really crowded. Okay, but we can't really measure that. We say 100 people per pool. Okay, now we're getting somewhere. And then down here, we've got something that we would call percent by mass. So we're saying if you take the mass of everything in that pool, including the water and the people, okay, so that's the total mass, okay, and you divide that into the mass of just the people alone, you're going to get a percent by mass. It's going to be 20% of that pool is people. And that would be a very crowded pool, okay? But the point I'm trying to make here is simply that there's different ways of describing concentration, and we've only mentioned a few of them here. We're going to go into about 5 different ways of describing how concentrated a solution is, okay? But before we do that, I just want to quickly review some terms around solutions. We talked about this, I think, in the first unit of the year. And so we're going to expand on it just a lot, really expand. We're just going to review really quickly. Okay, so here's some terms we need to know. First of all, solute. Okay, now solute is, now in our example of the pool, the solute would have been the people. But now let's use a little bit more of a chemistry example. And let's use salt water, since it's a very familiar concept here. And our salt water, our solute in salt water is going to be the salt, which of course is NaCl. Okay, that's the solute. The solute is it's oftentimes the solid that is getting dissolved. Okay, that's the solute. Now the next thing is what's called the solvent. The solvent in the case of salt water would be the water. Okay, and then let's look at one more term, the solution. That is the salt plus the water. Okay, it's everything together is the solution. Okay, now we will get into something a little bit separately where we talk about why things dissolve and what makes them dissolve easier and what makes more dissolve and less dissolve. But for right now, I just want to just review a few terms here when it comes to something we call homogeneous mixtures. You'll remember that homogeneous mixtures are just evenly mixed mixtures, essentially, like salt water. And then the other term that we know is heterogeneous. Hopefully these sound like a review. I'm sure they will. I know my handwriting's getting pretty sloppy here. We're just going to put unevenly mixed. Okay, and here's an example here I always like to use, just a simple one, pond water. It's always easy to use an extreme example, but we all know that pond water, when we take out a cup of pond water, it's going to be different in all different parts of it. If we take a sample from one part of the water, we might have a lot of bugs in it. Another part, we might have a lot of sand in it. Another part, we might have a lot of leaves in it. Whatever it is, it's going to be a variety of concentrations in different parts of it, where a homogeneous mixture is very evenly mixed. The concentration is going to be the same. The composition of the solute and everything is going to be the same no matter where you sample that solution. I'm going to mention just one more here, one more term that you just are going to see, especially if you are reading the book. A colloid. What a colloid is it is an evenly mixed mixture, so it's similar to a homogeneous mixture. But the difference is this: it has the solute is large particles. Okay, so once the particles get to a certain size, they start to call it a colloid. Okay, so things like milk could be a colloid because milk has kind of big chunks in it, in a sense. There are, several other things that would be colloids, especially things that are not easy to shine a light through. That's usually a good example that you probably have a colloid, where something like salt water, you could put a beam of light through it and it'd travel right through, without showing the little particles as it goes through. So that kind of gives you an idea of some different terms around mixtures that we're going to want to be familiar with. Okay, now I'm going to move this down just a little bit here. Okay, so this is the part where you want to pay close attention, but I'll also tell you here, I wouldn't try to necessarily, beat your head against the wall trying to memorize every single one of these. It's something that would be good to write on your note card. I'm going to show you the one that you for sure need to memorize. Then the other ones, if you have them on your note card when you take a test, that's okay. You don't need to necessarily have these down back and forth. Okay, so we're going to use this example of salt water just so that we are sticking with sort of the same idea here. And so that's NaCl. And let's just play like here we've got, let's say we've got 15 grams of NaCl. And let's say that it's dissolved in water, okay? And the water, so we've got the solution, let's say the whole solution is 100 grams. And the solution is the water plus the NaCl, okay? And let me just put one more way of putting it. Let's say the volume of the solution is 100 milliliters. Okay, so this is just going to be for our example. So as we go through each of these ways of measuring concentration, we can use this example and kind of let us explore these different ways of describing how crowded, in a sense, our beaker is. Okay, how crowded that cup of water is with salt in it. Okay, so the first way we can talk about how crowded it is, or what the concentration is is something called percent by mass, okay? Now, percent by mass is just the mass of the solute, our solute is salt, divided by the mass of the solution multiplied by 100%, okay? Now, the one thing you have to be really careful of when you look at this is it is the mass of the solution here, okay? That is the key. The solution is not the mass of the water. It's the mass of the water and the salt put together. Okay, now that's a really critical point, okay, that we cannot miss, okay, because if we just put the mass of the water on the bottom, we're going to get the wrong concentration. It's going to be very different. All right, so let's figure out the percent by mass. We're going to be, this is pretty simple stuff, so you guys will pick it up quite quickly. First of all, the mass of our solute, we're going to put all of this over here, okay. The mass of our solute is 15 grams, okay. The mass of our solution, look at that, we've got the mass of the solution right here, that is 100 grams, cancel, cancel, times by 100%, and our percent by mass obviously is going to be 15%, okay? And that makes sense. So you take the total mass. Whenever we take the percent of anything, we've talked about this, the percent is always X divided by total times by 100%. And all you're doing really here is you're just changing whatever that X is. The X is just whatever you're interested in. In this case, when we're talking about the concentration of sodium chloride, the percent by mass, we're talking about the X would be the sodium chloride divided by the total. The total mass is going to be the mass of the entire solution, and it's going to say that 15% of that solution is made up of sodium chloride, okay? Not too difficult, all right? Now, the next one is percent by volume. I'm not going to do an example here, okay? But I just want you to be aware of what this is. We just don't want to spend the time on the example because I think you'll catch it really quickly. Percent by volume is the volume of the solute. So instead of the mass of the solute, it's the volume divided by the volume of the solution. I will mention this is common if you are ever looking at something like a lot of mixed drinks or something like that. We'll say like it's 5% ethanol or something like that. Okay. So that would mean that the percent by volume is 5%. And so what that essentially means is if you take the entire volume is 12 ounces, then the volume of the ethanol would be 5% of that. Okay. And I'm not figuring it out right here in my head, but it's somewhere around a half an ounce, or a little more than a half an ounce, or whatever else. Okay. And so that's just percent by volume, just the volume of your solute divided by the volume of the solution. You most commonly use percent by volume when you've got two liquids that are mixed together. Okay. Whereas if you had a solid dissolved into a liquid, percent by mass would probably be more appropriate. Okay. So just be aware, again, I would write these down, and when you need to use them, just use them exactly like it says there on the chart. And just be careful that, especially when you talk about your denominator, if it says the solution like this, that means you don't just put the solvent, you have to add the solvent and the solute. It's the total solution is what you're looking at. Now, we're going to get on to the most important one, molarity, okay? This is the one that you will use over and over and over again in chemistry. It's the most common one to use, and it's also something that is relatively easy to measure in a laboratory setting. And it's really handy because when it comes to our stoichiometry that we're going to be using a lot, molarity is the concentration that makes the most sense to help us in figuring out stoichiometry. Okay, so in the case of molarity, it's going to be moles of your solute divided by liters of your solution. Okay, so it's moles per liter. Now I'm going to put one more thing here, a big M. Okay, that's the symbol for molarity. But when you see a big M, you have to think to yourself, this means moles of solute divided by liters of solution. All right, now let's go to our example here. Okay, so what we can do here is we can say, okay, we've got 15 grams. Now watch how we do this. We're going to do this in kind of a dimensional analysis way. But we want to figure out the molarity of this solution up here. We've got 15 grams of NaCl, and we put that over 100 milliliters of the solution. Okay. Now, what we can do is we can do this just like dimensional analysis. Okay, so we're going to go like this. And our goal here is, right now we're in grams per milliliter. That's not what we want. What we want is moles per liter. Okay, so all we do, and I'm sorry about it being just a little bit sloppy, but you'll get the point at least. We first need to take this NaCl and we need to turn it into moles. Okay, and so how do we go from grams to moles? Well, hopefully we've got that down by now. Whenever we're trying to go from grams per mole, we're going to use the molar mass. Okay, and I know you guys know how to figure out the molar mass. If you didn't, I would go and I'd show you a periodic table and how to do that, but I know I've already got this noted beforehand that for NaCl it's 58.44 grams per 1 mole. Okay, so that's going to be the molar mass of NaCl. So we can cancel out the grams. And then, so now we've got moles on the top, but look at this, we still have milliliters on the bottom. So we need to convert milliliters into liters in order to get moles per liter. So we need to do a conversion here. We know that there's 1,000 milliliters, hopefully we all know that, per 1 liter. Okay, now we cancel out milliliters. Okay, and now once we do our math, we're going to have liters on the bottom and we're going to have moles on the top. Every other unit we've now canceled out. So we have reached our goal. So that means we do our math. Okay, I'm going to pause the video for 1 second and then I'm going to come back and have our answer. So you can do your math as well while I'm doing that. And the answer we get here is 2.5 moles per liter. Okay, and so here's how we would write that. We would write, so we write instead 2.5 big M, which is the same as 2.5 moles per liter. And this is what we call molarity. Okay, so that's a very, very common way to measure concentration, the most common that you'll find in chemistry. Now I'm going to read you the last two here, and the name of this next one is extremely unfortunate, I would say. The next type of concentration is called molality. Okay, why on earth, whoever came up with these names in chemistry, I'm not sure who it was, why on earth they came up with one called molarity and one called molality, I have no idea. That seems like a horrible idea. I'm sure they could have found many more letters in the alphabet that don't sound so much alike, like mole solvent or something. I don't know exactly, but we could have come up with some other term. But for some reason, they came up with molality, all right, which sounds very much like molarity. Very unfortunate, but nonetheless, they do have a very clear distinction in their meaning. In molality, what it refers to is moles of solute divided by kilograms of solvent. Okay, and there's a good reason for this measurement. I'm not going to go into it right now, but there are reasons to use each of these measurements, and there's value in each of these measurements. And molality, I'll just tell you one place it has great value is when you have a solution that changes volume based on the temperature. Okay, this is actually one of the things that they say even with gasoline, is if you get your gasoline when it's cool, you're going to get more gasoline because gasoline slightly expands when things are hot. Okay, that would be a good example where molality is helpful, because even if the solution expands, the molality is the same, whereas the molarity changes slightly, because as you can see, if your volume goes up, if your liters of solution increases a little bit, your molarity is going to go down even though you have the exact same solution. And that's kind of the reason we have molality. Again though, it's molarity we care about, not molality. All right, wow, it would be wonderful to have a slightly more distinct term there. All right, finally, mole fraction. Mole fraction is just what it sounds like. It's just the fraction, what fraction of the moles are the one you're interested in, okay? And in the case of mole fraction, you take your moles of your solute, okay, and then you divide that by the moles of your solute plus your moles of your solvent. In other words, the total moles, you divide that by the total moles in your entire solution. So moles of solute divided by the total moles in the entire solution. So again, we had molality earlier. Now we've got mole fraction, which is moles of solute divided by the total moles in the solution. So that's just what it sounds like. You don't multiply this in by 100% because you're just leaving it as a decimal. So it's wouldn't be a big deal to multiply it by 100%, call it a percent, a mole percent, or percent by moles. But it just happens in mole fraction, they just leave it as a decimal, not multiplying by 100%. So again, write these down. Just get to where you know how to use them, but don't get overly concerned about memorizing them, okay? Except for get very, very, very familiar with molarity. That is the one that you want to be very confident on. And anytime something asks for molarity, you know exactly what it's talking about. You can calculate it. You can use that calculation in other problems. It's really important that you have that one down very well. All right, okay, now let's go ahead and we're gonna do 3 problems. Hopefully we can wrap this up within about 10 minutes, but we're gonna do 3 problems that will help us to understand these concepts. Okay, let me just get this a little clearer here. Okay, so the first problem here, let's just read it out. It says, in order to maintain a sodium chloride concentration similar to water, an aquarium must contain 3.6 grams of NaCl and 100 grams of water. What is the percent by mass? We're looking for percent by mass. That's key that we have to look for, of NaCl in the solution. Now, here's what you want to do is every time you get a problem like this, don't just say, oh, obvious, obvious, until you really know it, okay, because it might become very obvious after some time. But what I recommend is for the start, when you're doing these problems, you look at it, and if it says percent by mass, then you're going to go back up to this chart right here that you just saw. Sorry, we got up here. You go back up to this chart and you look at percent by mass. Okay, it says it's the mass of the solute divided by the mass of the solution times by 100%. I'm gonna actually just write that down on this next page because that's critical, okay? So the mass of the solute divided by the mass of the solution times by 100% is equal to percent by mass, okay? Sorry about the sloppy handwriting, but hopefully it's pretty clear what we're saying there. So this is going to be the formula that we're using. And remember, just refer back to these. Make sure you have it clear. Make sure you're solid on these, okay? So the first thing we do, all we do is really simple here. We just take the mass of the solute. That's easy because that's 3.6 grams of NaCl. Divide that by the mass of the solution. Okay, so we've got 100.0 grams of water. So that's the question. Do we write 100.0 grams of water in the denominator? The answer is, wait a second. It says the solution. The solution is not just the solvent. It is the solvent plus the solute. It's the total mass of that solution. So we have to take 100 grams of water and add to that 3.6 grams of NaCl. So we're dividing not by 100 grams of water because that would just be the solvent, but instead 103.6 grams of solution. So 103.6 grams of solution. So this is essentially the total mass of our solution. I'm going to multiply that by 100%. And I am going to pause for just a second and we'll do that on the calculator. Okay, and as an answer we get 0.0348 times by 100%. And that's going to come out to be 3.48%. So this would be our percent by mass NaCl in that solution, okay? And technically we would round that to only 2 decimal places because we have 2 decimals there, so that'd be 3.5% NaCl. Now just to be clear, had you put 3.6% NaCl, that would have been incorrect in this case, okay? Because you need to make sure that you use the entire solution in your denominator. All right, the next problem is going to be about molarity. Okay, now this is if you ever get an illness, you might go into the emergency room, and they might give you an IV, as they call it. And a lot of times it'll have sugar in it. Okay, now the picture is not really relevant. That's more about giving blood. But sometimes what you're actually doing is you're being fed through an IV. So you have a bag of solution that oftentimes has sugar in it, and that's flowing right into your blood, and that's really helpful when you're very sick, if you had a lot of vomiting and things like that. So, but we have a question about that, and this is going to be very common if you're looking at nursing or medicine or something like that. You're going to be figuring out problems like this quite frequently. So this one says, a 100.5 milliliter intravenous solution contains 5.1 grams of glucose. Okay, what is the molarity of this solution? All right, now let's go back and let's look at what molarity is. This is the one that we should absolutely have memorized. Let me go back the other way. Okay, here is molarity right here. Moles of solute divided by liters of solution. All right, let's go back. Okay, I'm going to write that up here. Big M, that means molarity, is moles of solute divided by liters of solution. I'm having a hard time writing here, obviously. Liters of solution. Okay, so this is what we're going for. So here's a way to do this with dimensional analysis. Okay, all we do is we start off with what our measurement would be of the glucose divided by the solution, and then we're going to convert our units to where it matches up correctly with what we have for molarity, which is moles of solute per liters of solution. So let's start off with, now to start, we have 5.10 grams of glucose, C6H12O6 per 100.5 milliliters of solution. Now look, this is the entire solution here. So we don't have to add anything else to it. If that would have said solvent, then we would have to say, wait a second here, I've got to include the solvent and the solute in my denominator when we're talking about molarity, okay? Because we're talking about the solution, not just the solvent, okay? But in this case, they've already taken care of that. We have the volume of the solution, which is 100.5 milliliters. So now all we need to do is we need to just extend this out, and we need to convert this into moles per liter, okay? Because that is the measurement for molarity, okay? So now we can just do a really quick thing here. They actually help us out here. Look, they say that they give us the molar mass. Okay, so we've got to go 180.16, that's a zero, doesn't look like it, grams per mole. Okay, and then we can cancel out grams. And then our solution here is in milliliters, but we needed to have it in liters. So we put 1,000 milliliters on top, divided by 1 liter. Okay, milliliters cancels out. And now we're left with liters and moles. So now we have our unit cancellation now is successful. All we need to do now is the math, and we should be able to figure out an answer for this problem to figure out the molarity of this solution that has 5.1 grams of glucose per every 100.5 milliliters in this IV. So I'm going to do that, and I'll come back in a second. Okay, that came out to be 0.2817 moles per liter. Okay, and let's just look here. We've got 5, so we should only have 3 significant figures, it looks like, so we're limited by this number right here. So that comes out to be 0.282. Now, instead of moles per liter, what can we write? We can just write a big M for molarity, okay? So that's 0.282 molar. This is how you actually say, you say it molar for molarity. You say 0.282 molar glucose solution. And this means, just so we're really clear, this means 0.282 moles of glucose per liter. Okay, and now we've just figured out the molarity of this IV that's going into some sick patient. All right, now the final problem we're going to look at is, oh, actually, we have a blank page here, and it's for a reason. I want to go over one more concept here, and then we're going to go into our final problem. Now, the next concept is this. Okay, you guys have all seen the yellow cabinet in the back of our lab that has all of those. We call them stock solutions. I'm going to write that down right here. Stock solution. Okay, and some of those stock solutions, they might be 6 molar HCl. You guys have probably seen this already. Now we're going to find out what that means. Okay, so that means it's 6 moles of HCl per liter of solution. Okay, that's exactly what that means. It could say 3 molar MgCl2. Okay, and of course that would mean 3 moles of MgCl2 per liter of solution. Okay, so the problem is, and this is a very common problem. This is not an unusual scenario because I actually have to do that frequently myself. We might have a lab that requires 2 molar HCl instead of 6 molar HCl. Okay, so somehow we have to get from a very concentrated HCl to something that's not as concentrated. This is a very similar idea in the example we used of Kool-Aid at the start. Okay, sometimes Kool-Aid is very strong. You taste it and it's like, oh, that's just too much. I need to dilute it. Okay, when you dilute something, then you add water to it. Okay, and by adding water to it, you make it less concentrated. Okay, or more dilute. And in the case of the Kool-Aid, maybe it'll taste better if you dilute it a little bit, if you overdid the sugar or the mixture. Okay, now there's a very, very handy formula, and it's a very simple formula. Okay, and it's the reason it works is, you know, if you look at it for a second, you'll see why it works. It's nothing mysterious, but it's just like this. It says sorry, just one second. Let me reverse that. Just one second here. Oh, weird. It doesn't allow me to reverse that. So just one second here. I'm going to erase that. Okay. All right. So we've got M1V1 equals M2V2. Okay. So write that down. I did it correct this time. So let me just clarify what this means, and I'll show you how it works in a problem. Okay, and I'll show you it as a problem that we commonly use here. M1 refers to the concentration in molarity of our stock solution. So stock solution concentration. Okay, so this is another way to think about this. This is the concentration of our solution to begin with. That's why we have the 1. The 1 we can think of as, what's the concentration when we start? In our example of the Kool-Aid, that would be the concentration of the Kool-Aid before we dilute it. This would be the concentration when it's very strong. Okay, now V1 refers to the volume of our stock solution. Okay, and in our case of our Kool-Aid, that would be how much Kool-Aid you start with. Okay, maybe you have a half a cup. You're going to dilute it to a full cup. Okay, and so that's the volume of the stock solution. So it's the volume of the stock solution that we use when we dilute it to the final volume that we want to achieve for our lab, let's say. Okay, and then as you can kind of suspect here, the M2 refers to the molarity of the, so just to clarify, going back just a little bit here, when we said the concentration down here, the big M, this of course referred to molarity. I'm just going to put in parentheses here that this is molarity. And now the final M here, this refers to the molarity of our diluted solution. And then the volume 2 is our final volume, the volume of the diluted solution. Okay, so again, when you see the little 2 here, what that's really referring to is the diluted solution. If you see the 1, that's referring to our stock solution or our original solution, the solution before we diluted it. Okay, and we'll show you how this works in the next page, and this will be the final problem, and then you're all set here. Okay, so here is how we do this. Okay, so if you know the concentration and volume of the solution you want to prepare, you can calculate the volume of the stock solution you will need. Okay, so this is a case where we have something we want to dilute. Okay, and we say, okay, I want a, let's just imagine here. In fact, I'm going to put this little example here. Okay, so here's how it works. We have, first of all, we have a, this is looking a little ugly. Let's try to delete this really quickly. Okay, try this one more time here. Okay, this is our graduated cylinder here. Okay, and we have our stock solution. I'm going to put it as a little container here. Okay, and we're going to make it look like a bottle because they oftentimes come in a bottle. Okay, so that's our stock solution. Okay, and this is our graduated cylinder. Okay, so what happens when you dilute a solution? You take a certain amount of your stock solution, you pour it into your graduated cylinder, which of course has all of these marks to figure out how much you get. And you pour in, let's say you pour in a little bit down here, okay? And so let's say you put in the solution, you put a little bit of it down here. So I'm gonna put a different color here. Let's see, you put a little bit of it down here on the bottom. Let's say you put it up to right here. This is your stock solution. And then you take some water and you put some water in here and you're going to dilute this up to, like, let's say right here. And of course, the effect is that you now have a less concentrated solution because you've taken the more concentrated stuff over here from your stock cabinet and then you've diluted it with water. This would be the same example if you had your really concentrated Kool-Aid. You'd put a little bit here on the bottom and then you dilute it to whatever your final volume is that you want. But you want to make sure that you're getting the right concentration. So we're just going to show you how to do that. Okay, so I'm going to erase all of the solution here so we can do this here in a second. Okay, so here's how we do it. Okay, so what volume in milliliters of 2.0 molar calcium chloride stock solution would you use to make 0.50 liters of 0.300 molar calcium chloride solution? Okay, so here's how this works. We have, first of all, our stock solution we see here is going to be 2.00 molar calcium chloride. I'm just going to write this on here so we're really clear here. We're talking about CaCl2, and it is 2.00 molar. That is our stock solution, okay? But for our lab, we need a half a liter of 0.300 molar solution. So we have to find a way to dilute this concentrated calcium chloride to where it is a half a liter of 0.300 molar calcium chloride. So much less concentrated, okay? So here's what we do, okay? We take, I'm gonna go back to my yellow here. We take our formula, M1V1 equals M2V2. Okay, we take our formula. Okay, first of all, we're going to be solving for the volume in milliliters of the stock solution. Okay, so we've got to be solving for the stocks, how much of the stock solution we need. Now remember, the stock solution is the number 1. It's our initial solution. Okay, this is referring to the stock solution. So we're going to be solving for V1. We want to know how much of this calcium chloride we put into our graduated cylinder before we dilute this to 0.50 liters. Okay, so we solve this for V1. So let's just, before we put any numbers in, let's isolate V1. Okay, so we just cancel this out and we come up with this. V1 is equal to M2 V2 divided by M1. Okay, so now we've already solved for, we've already isolated our V1. Now we just substitute in our numbers. Now, one thing I want you to make note of here is we want our answer to be in milliliters. Okay. Okay, so, but the measurement for our final solution is in liters. So we need to change liters into milliliters. Let's do a really quick conversion before we cancel these in, or before we substitute these in here. We've got 0.50 liters. Let's convert this to milliliters, okay, just so that we're working in milliliters, and you'll see why. We could have converted this at the end. That would be fine too. We're going to do it right now, though. 0.50 liters to milliliters. Okay, all we need is a conversion factor here. And we know that we have 1,000 milliliters per liter. Cancel out the liters. And then we're going to get 0.5 times by 1,000. It comes out to be 500 milliliters. Okay? All right, awesome. So we know that we have 500 milliliters. This is our final solution. This is going to be V2. Okay, so it's going to be our volume of our final solution. So let's substitute in each of these numbers, and then we can crack this problem here in just a second here. So let's substitute in. We're going to substitute in for V2. We're going to put a same equals here. So V2 is going to be 500 milliliters. Okay, our M2, so that's the molarity of our final solution, is going to be 0.300 m, okay, and we divide that by, put little parentheses around those, we divide that by the concentration of our stock solution, because we've got the 1 next to it. The concentration of the stock solution is 2.00 molar, okay, and then we do that math, and we're going to get the volume of our stock solution that we need to pour in is going to be, let me pause this for a second, I'll do the math and I'll come back. Okay, this is going to come out to be 75 milliliters. Okay, so let me just tell you what this means, and pay very close attention to this part, because this is the part that I find people kind of have a hard time right at first. It's not complex, but it's just, you know, figuring out where this all fits in. Again, this is the amount of the stock solution we need to use before we dilute the volume to our final volume, okay? So in this example, okay, let's say we're going to make our stock solution a different color here. We'll say that this calcium chloride, I'm not even sure what color it is, but we're going to say it's kind of a pinkish color, okay? So this calcium chloride solution, you'll see, we're going to make it really clear, this is kind of a pink colored solution in here. Okay, so what we do is we fill this in until we get to, we'll say that this is, so we're pouring this in like this. Okay, we fill it up until it gets up to 75 milliliters. All right, then what we do is once we've poured our stock solution in, then we take some water and we fill up, let's get that here. We fill up the water all the way up to our final volume, which is 500 milliliters. Now, I know that the scale's not right here and everything else, but we're going to play like this is 500 milliliters. So we fill in water on top of it like this, all the way up to 500 milliliters. And you really should even mix these together, because it all gets mixed together very quickly, obviously. Okay, and then once we have filled that up and we followed these instructions, we put in 75 milliliters of our stock solution, and then we dilute it to our final volume, which is 0.5 liters, which is the same as 500 milliliters. Just do that conversion. We already did it over here. Okay, once we fill that up, okay, then we know based on this formula here, M1 V1 equals M2 V2, we know that our final molarity is going to be 300 molar. Okay, so we have a way of using our stock solution to prepare a solution that's 500 milliliters with a concentration of 0.300 molar. Okay, just one second here. We got to get that dot out of there. That's annoying me. Okay, so 500 milliliters of our 0.300 molar solution. And that is how you use this formula. Okay, again, this is the final time I'll mention it. The 1 refers to your stock solution. The 2's refer to your diluted solution. Okay, and if you keep that straight, you're going to be in pretty good shape on these. All right, well, I hope that made some sense. And you're welcome anytime, hopefully anytime this week, you can come in. Second block if you need to, first block even if you have to, third block of course, and fourth block. Come in any of those times and we can work together through the practice problems that we've given you in Canvas. But other than that, I hope you have a great day and hope you enjoyed learning about concentration.